Suppose you would like to invest, and investing in real estate might seem a good idea. But you're uncertain. Is there anything you could do? With investing, you are taking risks, and just relying on a single risk model may give you a false sense of security. The take-home message for investors from this video is that using Bayes' theorem could act as an early warning system. Hello, my name is Romke, and this video is all about data, models and uncertainty, all from a Bayesian perspective. Bayes' theorem is a language for expressing uncertainty. As an investor, you should have a gut feeling about the market. This is expressed by a prior distribution. The returns of a specific property goes into the likelihood. Combined, your knowledge about the market and the property returns gives you an updated belief in your property. This is the posterior. The prior, the likelihood and the posterior gives you the evidence, and the evidence is a measure of your confidence. Let's look at some data. Here we have 11 years of annual returns of a property. These are actual data. The annual return is a ratio and it's accounted for yearly. It's the net income of a property plus its change in market value divided by the current market value. In the annual returns of this property we see a flat period over here and some real-world variations, especially these last 4 years. Let's try to model the data using some familiar tools, the least squares fits, and we have fitted a straight line and a cubic polynomial. But neither model is very satisfying. Data are never exact. Every return value has a little bit of wiggle room, and this uncertainty matters. We show the uncertainty by error bars. But here is the thing. In real estate, the uncertainty rarely follows the familiar bell curve or Gaussian distribution. In this video we call the Gaussian distribution the normal distribution. What does uncertainty look like? The yellow histogram shows the distribution from all annual returns in the market. Some properties are highly profitable and some perform rather poorly. We fit 4 different distributions to this histogram. The normal distribution, logistic, student and Gaussian distribution. And each have progressively fatter, heavier tails. These tails represent the rare events that make risk unpredictable. Next, we will combine the linear and cubic models from the previous slide with the 4 uncertainty distributions, and thus we get 8 possible models for fitting the data of a single property. The likelihood of Bayes' theorem captures the data, the uncertainty as well as the polynomial model. With 8 models we have 8 likelihood functions for a single property. The figures show the maximum likelihood fits, 4 for the linear model on the left and 4 for the cubic model. None of these models seems to capture the annual returns really well, and there is a good reason for that. How about the market? There is also uncertainty in the market as a whole. Our market consists of about 250 properties. Our belief in the performance of the real estate market is captured in the prior distribution. I'm leaving out a lot of details, but here are the distributions for the linear and cubic model. The purple lines represent the most probable model for the prior, and the shaded areas indicate the uncertainties in the prior distribution. Overall, the market is going down, but the two priors have a different spread in uncertainty. Earlier I told you that your beliefs in a particular property would be updated after taking the market into account. So updating the likelihood by the prior gives the posterior distribution. Here are the 8 maximum posterior models. However, there is not much improvement. In each panel, the models seem to have converged somewhat when compared to the maximum likelihood models, but actually no model is convincing. There is definitely something missing in our modeling of the real estate property. And despite that this is fully Bayesian, your confidence in our results is probably not very high. Now recall that the confidence came from the evidence factor, which is the next subject. Now we come to the essence of Bayesian modeling. Each model has an evidence value, and the numbers will be shown shortly. The model with the highest evidence value is the best model. But we are ranking the models by the differences in evidence value between the best model and any alternative. These differences are called Bayes factors. A Bayes factor quantifies how strongly an alternative model is supported relatively to the best model. The Bayes factors are summarized in 5 categories. For example, a model with a Bayes factor between 0 and 1/2 is essentially equivalent to the best model. Models with higher Bayes factors are progressively worse. In what follows, we focus on the Bayes factors in these categories. For our property, this table shows the evidence values of all 8 models. And the table is ordered by the value of the evidence. The differences are shown here in the Bayes factors, and the categories from the previous slide are indicated here. For this property, the Gaussian linear model has the highest evidence and is therefore the best model, while the Gaussian cubic model is an equivalent model with only a very small difference. The models with the student distributions, linear and cubic, are in the bad category, while the remaining models have to be outright rejected. This raises the key question: why do the commonly used normal distributions perform so poorly? But what about another property? The corresponding data will be shown shortly, but here all 8 models are essentially equivalent to the best model. The student T cubic model has the highest evidence, and all other models are essentially within 1/2 of the Bayes factor. This table and the previous table illustrates the model ranking concept. But how can we understand these tables in terms of the data, the models, and the uncertainties? Let's return to property number 1. On the left, we have the best model, the Gaussian linear model, and on the right, for comparison, the normal cubic model. The blue lines are the maximum likelihood, the purple lines are the maximum prior, and the red lines are the maximum posterior, solutions. Thus far, the models shown were obtained from the maxima of these distributions and therefore effectively ignoring the full distributions. And the full distributions are shown here. Now we clearly see the differences in the fat tails of the Cauchy linear and the thin tails of the normal distribution. One has to read these figures vertically as a density on a vertical line. On this vertical line we have the maximum of the posterior here. We have the 68% density in this shaded area and the 95% density in this shaded area. And the same for the normal distribution. The maximum of the posteriors here, 68% is here and 95% is here. In the left panel we see that the Cauchy distribution is the only model which can accommodate the variability in the data through its extremely wide tails. And therefore this model emerges as the best model. On the right, the commonly used normal cubic model is much narrower and essentially misses these three values. Technically, these widths are called the predictive distribution. Property number 1 was deliberately chosen to illustrate poor model performance. But what does a well-behaved case look like? For property number 2, the student cubic model has the highest evidence, while all other models fall into the so-called equivalent category. As we can see here, the predictive distribution from two of these alternative models essentially coincide. They are, for all practical purposes, indistinguishable. Let's now scale up to the entire real estate market. We now compare the base factors across all properties. For each property, remember, we have 8 models and therefore 8 base factors. We count for each property how many models are essentially equivalent to the best model, or in other words, how many have a base factor for that property smaller than 1/2. Just as we had 2 equivalent models for property number 1 and 8 for property number 2. Roughly 70% of all properties have 6 or 7 or 8 models essentially equivalent to the best model. Property 2 was in this group. About 20% have 3, 4 or 5 models equivalent to the best model, and about 10% have only 1 or 2 models equivalent. So what does this mean, and how is this related to risk? This figure summarizes all our results. It shows the base factors for all properties and for all models. Here are 8 bar charts stacked on top of each other, one for each model. The normal linear, the normal cubic, and so on to the Gaussian linear and Gaussian cubic. Horizontally are the percentages based on counts of the properties. On the right is the color coding for the base factors. Yellow are the best models, green are the equivalent, the darker greens are the poor and the bad models, and the dark blue are in the reject category. Every single property has 8 models and thus 1 count in each of the rows. Property number 1 had its best model in the linear Gaussian group and therefore 1 count in this bar. Its second best model was the Gaussian cubic model and therefore a count in this bar. The student models were both in the bad group and therefore have 1 count over here, and the 4 other models were in the reject group. property number 2 had its best in the student cubic, which is over here, one count here, and all 7 other counts in these light greens equivalent models. As we can see, about 70% of all properties fall into either the best or the equivalent group. There are some 20% which are over here in the darker greens, and 10% are just difficult to model. Some of these properties might benefit from the wider tails in the uncertainty distribution, as our property number 1. For those properties with several Bayes factors in these darker areas, this analysis may serve as an early warning signal for higher business risk. However, with our Bayes factors, we have arrived at the limit of the Bayesian analysis. In the end, it delivers just a probability distribution, and translating these insights into concrete investment decisions requires much more, for example, a loss function and a decision strategy, but that is beyond our present analysis. It's time to conclude. We've presented a fully self-contained Bayesian framework for model ranking based on real data. The take-home message for investors and perhaps others is that beyond the normal business risk, there is an additional uncertainty in the modeling. Just considering a single model may give you a false sense of security. But perhaps the good news is that a risk assessment based on Bayes factors could act as an early warning system. Apologizing for my Dutch English accent, and on behalf of our team, I thank you for your attention.